In kinematics, we measured how things move, tracking velocity and acceleration. But to understand why they move, we have to look at the invisible pushes and pulls acting on them, forces. The bridge between forces and motion is Newton's second law. The sum of all external forces on an object equals its mass times its acceleration. This single equation serves as the starting point for every dynamics problem we solve. To map the physics, follow these strict rules for free body diagrams. First, isolate the object as a simple dot. Second, draw only the external forces acting directly on that object as arrows pointing outward. Here we see the definitions for the most common forces. Weight is the pull of gravity acting straight down. Normal force is a contact force exerted by a surface, always pointing exactly perpendicular to that surface. Let's put this into practice for a block being pulled across a flat floor. We start with our central dot. Gravity pulls down with weight. The floor pushes back up with normal force. The rope pulls right with tension, and sliding across the floor generates friction, acting parallel to the surface to oppose the motion. With the forces mapped, we translate the visual diagram into algebra. Because forces are vectors, we split Newton's second law into two independent tracks, one equation for all the horizontal forces along the x-axis, and a separate equation for the vertical forces along the y-axis. Converting a physical scenario into a standardized free body diagram is the essential first step to solving any problem in dynamics. Things change when we move off flat ground. If a block slides down a ramp, standard upright x and y axes make the math difficult because the block's diagonal acceleration is split across both directions. To fix this, we align our coordinate axes with the motion. By rotating the x-axis so it runs parallel to the ramp, all the acceleration happens strictly in one direction, meaning acceleration in the y direction is exactly 0. This textbook image highlights the immediate benefit. Look at the right side. The normal force vector perfectly aligns with our new tilted y-axis, since it sits perpendicular to the surface. But remember, the weight vector, driven by Earth's gravity, still points straight down. Because weight no longer lines up with our tilted axes, we have to break it down into horizontal and vertical components using a right triangle. Placing your angle theta in the wrong corner is the most common mistake here. If you draw the ramp at an extreme angle, you can visually match the tiny sliver of the ramp's angle directly to the corresponding small upper vertex inside your SOHCAHTOA triangle. Once the angle is set, basic trigonometry gives us the components. The force parallel to the ramp is mass times gravity times the sine of theta. The perpendicular force pressing into the ramp is mass times gravity times the cosine of theta. By rotating the axes and resolving the weight vector, a two-dimensional diagonal motion problem becomes a straightforward one-dimensional calculation. Let's apply these rules to a multibody system. Block A sitting on a table, connected by a taut string over a pulley to a hanging block B. For interconnected systems, never draw a single combined free body diagram. You must isolate each object. On the right, block A gets normal force, weight, and tension to the right. Block B gets its own diagram, with weight pointing down and tension pulling up. Because the blocks are connected by the same taut string, the tension force acting on both blocks is exactly the same. And because they move together, the magnitude of their acceleration is also identical. Now it's your turn. Pause the video. Using only these two diagrams, write the sum of forces equation in the x direction for block A and the y direction for block B. These shared variables, tension and acceleration, are the physical links that allow us to combine our equations and solve the system as a whole. Let's check your work. For block A, the only horizontal force is tension, so tension equals mass A times acceleration. For block B, we take the downward force of weight, subtract the upward tension, and set that equal to mass B times acceleration. We now have a system of two equations. The cleanest algebraic strategy to solve this is to stack the equations vertically and add them together. When we do this, the math handles the internal forces for us. Because tension pulls in opposite directions across the entire system, the positive t and negative t perfectly cancel each other out. What's left is a single equation. The total acceleration of the entire system is simply the net external force divided by the total mass. Every dynamics problem you face will follow this exact checklist. First, isolate the object. Second, draw the external forces. Third, choose a smart coordinate system. Fourth, break your vectors into components. And finally, write out Newton's second law and solve. By methodically isolating objects and trusting Newton's laws, any complex physical system can be mathematically decoded and solved.